Hello everyone, in this lecture we will be solving Lemma 1.44 from Evan Chen's new book, New Euclidean Geometry for Math Olympians book, edition 2016. Here's a view of this problem. We are told that ABC is an acute triangle, and I have clearly marked those points ABC here. Let BE and CF be the altitudes of ABC, so you can see the foot of the altitudes clearly as well as the altitudes. Let me go ahead and mark the 90-degree angles over here. So this is 90 degrees, obviously. This one is also 90 degrees. Moreover, M is the midpoint of segment BC. So M, this point, obviously I have marked these equal line segment here. So therefore, BM is equal to MC as well. We would like to show that ME, MF, so ME, MF, and the line through A parallel to BC. So this line, which is somehow parallel to BC, they are all tangent to the circumcircle of triangle AEF. A is one of the vertices of our triangle. E and F are the foot of the altitudes on the edges that contain vertex A. First of all, from my rough sketch, I can kind of feel that the intersection of the altitudes, namely the orthocenter H, it looks like it lies on the circle. Is that so? Of course it is, because AFH plus AEH being those angles adding up to 180 suggests that AFHE is cyclic, so therefore H lies on the circumcircle of FAE as well. Not only that, but also AH, which is our altitude, obviously the altitude of our triangle. The portion AH is the diameter of that circle. But notice that let's call this point as D. AD is perpendicular to BC, but then it suggests that AD is also perpendicular to that parallel line to BC. Therefore, that parallel line to BC, let's call it line L, is perpendicular to the diameter. It must be a tangent at A. So that solves the second part here. We still need to show that ME and MF are actually tangent to our circle as well. So for that, what we need to do then, we need to show, let's start with ME first. To show that ME is tangent to our circle is the same as saying that ME, and let's call the center of that circle as, let's call it, I guess, K. So we would like to show that angle MEK is actually equal to 90 degrees. So we would like to show that that angle is 90 degrees. But then when we think about it, so let's draw this angle here. That angle being 90 degrees, when you think about the circumcircle, so we would like to show this angle MEK is 90 degrees, this angle over here. Think about the circumcircle of triangle MEK. Well, that one, what is it? M is the midpoint of a side line segment, and HA is the this line segment joining the orthocenter to one of the vertices. I know that circle very well, a circle which goes through the midpoint of the segment joining the vertex to the orthocenter, and the line segment which also connects the midpoint of the side. This is nothing but the diameter of the 9-point circle. So therefore the circumcircle of MEK is nothing but is the 9-point circle. That's a very, very surprising result for us. So not only that, but because it's diameter, so MK is diameter. We know it very well from our 9-point circle notes. Make sure you watch those videos. So therefore, because MK is the diameter of this 9-point circle, it must be that this implies angle MEK is 90 degrees. But similarly, it's not too hard from the same that F is also on that same 9-point circle. As a result, angle MFK is also 90 degrees. Therefore, both ME and MF, they are actually tangent to the circumcircle of AFE, and we are done.